Hello everyone, back to physics. Looks like we got Grace, Shocker Cat, and Katerina. I saw that Grace fell through the stairs today. That's good, you're okay. That's because the stairs, for whatever reason, could not provide the normal force to you. Probably a weakened wood something, or could not provide the upward force of your weight plus the force of pushing down on the stairs. So you could accelerate it through the floor. There's your physics lesson. See you all next time. Just kidding. So today we're going to talk about momentum. You've all heard of momentum before. Say, I've got a lot of momentum. Things are going well for me. Or that sports team has a lot of momentum, meaning they're doing well. They're going to be carrying through. So that gets its, the talk like that comes from physics. So momentum, let's talk about where it comes from. So remember Newton's second law, F equals ma. Now, we can't break F down into anything because we're just talking about a general force here. But we can break A down into something. So we have F equals m, and A, remember, is, oh, you can't even see that. Doggone it. A is Vf minus Vo over t, change in velocity over time. Remember that? So now we can multiply both sides by t and get Ft equals m Vf minus Vo. And this is where we get momentum from. This here is called an impulse. Force times the time it acts. And m, we can distribute this m. So we have mvf minus mvo. And this here is momentum final, which we call p, and this is momentum initial, which is p sub 0. So p is momentum. Again, I've messed up. Oh, heck, just leave it. Take this and move it a little bit. Impulse. Hey, Deborah. So P is momentum. And you also can see that it has the units mass times velocity. So impulse is equal to the change in momentum. So F times T equals delta P. The delta, remember, means a change in. So it's F delta T. Oh, we don't need that. Ft equals Pf minus Po. So this is called the impulse momentum equation. Stupid pen. So this is how rockets work. When they launch the Starship tomorrow, or they launched the Dragon a few months ago, any rocket, the engines are doing a chemical reaction forcing hot gas out of the rocket, which is the thrust, the force, over an extended period of time, right? You know, those rocket engines burn for a few minutes. And what is that doing? It's providing an impulse. Is changing the momentum of the rocket. The initial momentum of the rocket is 0. So this would equal momentum final minus 0. The tricky thing with this is the mass changes. Hello, Hero. That sounds good. Keep listening, Hero. This will put you right to sleep. The tricky part of this, like I said, is the mass changes. The mass of the rocket. Dillhole, what's up? The mass of the rocket initially, with the fuel in it, is at its maximum. As soon as it starts burning the fuel, its mass, the rocket's mass, starts to decrease. So the mass is not constant. And that's what you get into the rocket equation, which gets involved in calculus, which is too much, I think, for us to talk about today. Because I don't know if you know calculus or not, but I don't want to get into that if you don't. So this thrust is technically Newton's third law. So when the rocket engine is going up, here is the rocket. Here is the fire coming out. Your husband was a beekeeper. Interesting. The rocket is pushing hot gas this way. It's forcing hot gas this way. The gas then pushes this way. Gas pushes back, causing the rocket to go up. That's cool. Made his own honey. That's really good. So let's do a problem. You can't even see my drawing. Doggone it. So I'll draw a rocket here. Let's say this is a rocket pushing hot gas down. It's forcing it out the nozzles, and the hot gas pushes back. Newton's third law. Action, reaction, and that's what makes the whole rocket go upward. Alright, so let's do some problems here. Remember, I cannot go below a certain location. Oops. I'm going to change this stupid thing. Thank you, Deborah. Okay. So let's say that we have a flat surface, shapes, and we'll have two boxes on it. Call this M, and this 2M. And this one is moving this way, this one's moving this way, this is moving at V, this is moving at V over 4. What's going to happen? They're going to collide. There's a collision here. And we'll say that this is an inelastic collision. Inelastic collision is when masses collide and stick together. So think of a car crash. These cars hit, they get tied up together, and they move as one. That's an inelastic collision. So what is going to be the final velocity? Hey John, right? What is going to be the final velocity after the collision? Well, momentum is a vector. So F, we know force is a vector, time is not, equals M VF. I don't want to do that, never mind. Let's just do momentum. P equals MV. So momentum's a vector and velocity is a vector, so we have to include direction with this. So let's say it to the right is positive. And there's another conservation law, it's the conservation of momentum. That means momentum initial, the sum of momentum initial has to equal the sum of momentum final. Hey Ben, we're all good, how are you? Remember, the sigma means the sum of. So what's the initial momentum? Well, it's mass m times its velocity v plus mass 2m times its velocity negative v over 4. And afterwards they're going to stick together. M plus 2m times vf. That's good, Ben. So we can say we have mv minus 2mv over 4 equaling 3m times vf. We're looking for vf. So how will we go about solving this? Well, we can cancel out the m's because they're in every single term in this equation. So we get v minus v over 2 equals 3vf. So v minus v over 2, we're going to do subtract fractions. So 2 minus 1 is just v over 2 equals 3vf. We divide both sides by 3. Vf equals v over 6. There's our answer. So when they collide and stick together, they're both going to move to the right at a much slower velocity than either of them were initially. That makes sense. See, they collide bouncing off each other with no loss in speed because that's the next type of collision we're going to talk about, Deborah. That's called an elastic collision. This one's inelastic, where they're sticking together. But this is what police use when they're investigating crash scenes. They will measure the distance the cars were from like where the initial collision was to where the car stopped, skid marks on the road, etc. They'll measure that and they'll plug this into a bunch of equations and they can figure out how fast the cars were moving initially. There's a whole program in the police department to train the police that can handle the math to do this for the investigation. Now in this one, energy is lost. So kinetic energy is lost, always lost in an inelastic collision. Remember what kinetic energy is? Energy of motion. So let's see what our kinetic energy initial was. During that time, they can tell how fast they were going before the crash. Yes, they can. Pretty close. Yep. Kinetic energy initial is the kinetic energy of mass m plus the kinetic energy of mass 2m. So kinetic energy here is equal 1/2 mv squared plus 1/2 of 2m times v over 4 squared. Whole thing squared like that. So sum of kinetic initial 1/2 mv squared. Hello Genesis. This 2's cancel and we get mv squared over 16. So 1/2 plus 1/16. You gotta get a common denominator. I'm going to let the calculator do it. 1/2 plus 1/16. We get 9/16. We get 9 mv squared over 16. So that is a sum of the kinetic energy initial. Now we have to do the same thing afterwards. What's the kinetic energy final? We're running out of room here. We'll just say Vf is V over 6. We'll put it here. We'll get rid of this stuff at the bottom. We're running out of room. Delete. So let's see what the kinetic energy final is. It's just going to be 1/2 of the combined masses since they're stuck together, which is 3m. Times the velocity final squared, so v over 6 squared. So 3m over 2 v squared over 36. So the 3/36 we can simplify. I'm just going to do it in the calculator. 2 times 36. 24. What? That's not right. Fraction. 1/24. So mv squared over 24. So you can see we've lost kinetic energy. So this is 0.042 v squared, mv squared. And this is, hey Uranium Pride, 9 divided 16.56 mv squared. So you see we've lost a significant amount of kinetic energy. Now where does that energy go? Well, think about a car collision. When the cars collide, you hear it. It's loud. So sound is energy. So you lose it through the sound. You lose it through the destruction of the cars, the bending of the metal. That takes energy. So some energy is lost in that. It heats up the pieces that collided. Think about hitting a nail with a hammer several times. You'll feel the tip of the hammer or the nail to be hot. Heat is energy. So sound, heat, and actual destruction is where that energy goes. All right. Any questions before I erase all this? We'll do the next type of collision next. What's that super collider supposed to do? The super collider is taking subatomic particles like protons and neutrons. Actually, protons. I can't do it with neutrons. They take protons and they accelerate them to as close to the speed of light as they can, and then they collide them. And from what happens after the collision, there are fragments that come off of it, and they're looking for particles that make up the proton. Quarks, and they're looking for that, what they call the God particle, the thing that gives up all mass. Yes, Resident Evil just sucks. Resident Evil 2 is okay, but 4, garbage. 7 I think is good, because I think I've played it a little bit before. We'll get to 7 eventually, but the one last night, I'm not fooling with that. So they're trying to find out, Dillhole, what makes up matter. And they're looking for this, and they found it. They found traces of it. It's very hard to find. It takes many collisions over time to find it. Not really. Not really dangerous. The masses are so small that they've worried about creating many black holes doing this. And they think that the black holes, they feed on matter, so they're worried about creating these little mini black holes will start to eventually eat the Earth, and I think that's a little far-fetched. But it is expensive. What are they protesting, Iranian? Next type of collision. Let's deal with the next type of collision here. Whoops. They want the owners out from UTD. I think that the Liverpool team paid protesters to cancel the game because they're afraid they're going to lose. So we'll say this is M. We'll say this is 2M. and smashing everything. Oh geez. This will be V, and this will be V equals 0. This is all initially. Hey Greg. Wow, Ben, pretty serious. So they're protesting about soccer. So what happens when an object collides with a much heavier target which is at rest? Let's do that. Let's make this much heavier. Let's make this 10 times heavier. 10m. Let's give these numbers now. Let's say we've got 5 meters per second. What are the velocities after collision of both masses? Process against the owner. Okay. All right, this will be a lot more involved calculation here. So just hang on. To solve this problem, we know both initial velocities, right? So let's write that out. Momentum is always conserved in collisions, unless there's an outside force acting, which we will say there isn't. There's no friction or anything. Yeah, smart car versus dump truck, good. You can kind of imagine what would happen, right? The bigger mass isn't going to be moving very fast, but the smaller mass will bounce off. So let's show that. So the initial momentum is just m times 5 plus 10m times 0. And then afterwards we have m, we'll call it v1. Okay, I'll check it out later, Ben. Thank you. Plus 10m v2. So this will be an elastic collision. That's where they hit and bounce off of each other. They don't stick together. Think about cue balls. You're playing pool or snooker, the balls hit and they bounce off. So we have two velocities here. We don't know what they are. All the m's will cancel. So we get 5 plus 0 equals v1 plus v2. So 5 equals v1 plus v2. So we can't solve this because there's an infinite number of combinations of v1 and v2 that make this true. So we need another equation to solve this, and we could use kinetic energy. So let's do that. Since kinetic energy is conserved, it is conserved in this, so that means that the sum of kinetic initial has to equal the sum of kinetic final. So what is the initial kinetic energy? It's 1/2 of the mass m times 5 squared. Afterwards, it's 1/2 m v1 squared plus 1/2 of 10m v2 squared. So we get 25 over 2, which is 12.5 m, equaling 0.5 m v1 squared plus 5 m v2 squared. Now the m's will cancel again. So we get 12.5 equaling 0.5 v1 squared plus 5 v2 squared. So you can see now we have two equations with the two unknowns in it, so we can solve it. Okay, so let's solve this for v1. So v1 equals, subtract v2 from both sides, we get 5 minus v2. We're going to plug that in here. So we get 12.5 equaling 0.5 times 5 minus v2 squared plus 5 v2 squared. Now we have one equation with one variable, so we can solve this now. So we have to square this. You remember how to do that? Remember foiling? 5 minus v2, 5 minus v2. First term, FOIL. First terms, multiply them. 5 times 5, 25. Outside terms, 5 times negative v2 is negative 5 v2. Inside terms, multiply 5 and negative v2, we get negative 5 v2. And last terms, negative v2 times negative v2 is positive v2 squared. So we get 25 minus 10 v2 plus v2 squared. That goes here. But then we have to multiply by 0.5. So it would be 12 and a half. So 12.5 equals 12.5 times, or minus 5 of distributing the 0.5 through this whole thing, plus 0.5 v2 squared plus 5 v2 squared. So look at this. This cancels with this. And then, oh, it doesn't. Sorry, what am I doing? Wrong. Okay, these two add. So we get 12 and a half. It's 12.5. This adds, so it's plus 5 v2 squared minus 5 v2. This doesn't seem right. Something's wrong here. That is not right. I messed up somewhere. Figures, the phone rings every time. Always love to call. All right. The reason I know this is wrong is because this is going to add up to 0, which is not right. So what's wrong here? So let's go back. 1/2 of m times 5 squared is 25, plus 1/2 m 1 squared, 10m. So this is 12 and a half equals 0.5 v1 squared plus 5 v2. 12.5 equals 0.5 v1 squared plus 5 v2. v1 first, outside, inside, last. 12 and a half. Oh, duh. Wait a minute. 0.5, that's right. 5 minus v2. Okay, this is right. So 0.5 times this, 12 and a half. What in the world? This is why I don't like doing it this way, because it gets very messy. Alright, so the best thing to do when this happens is to start over. Instead of tracing all of your garbage, sifting through all of your garbage, you might as well just throw the garbage out and start over. Kids at school hate it when I do this. I'll just go up to the board and erase everything for them. Okay, MV, 5m, 10m times 0, m1, plus m2. Okay, so that's all good. Everything is good here. So kinetic initial, so sum of kinetic initial has to equal sum of kinetic final. So 1/2 Hey Jamie. 5 squared plus 0 1/2 m v1 squared plus 1/2 of 10m v2 squared. So 1/2 of 25m is 12.5, right? And then we get 1/2 mv1 squared plus 5 mv2 squared. Okay, m's are going to cancel. So 12.5 equals 1/2 v1 squared plus 5 v2 squared. We're going to multiply everything by 2 in here. So we're going to get 25 equals v1 squared plus 10 v2 squared. All right. So v1 is 5 minus v2. We're going to plug that in here. So 25 equals 5 minus v2 squared plus I think I see what I did wrong, maybe. 25 equals v1 is 5 minus v2 squared plus v2. Alright, I'm confusing myself here. Take these headphones off, this music's annoying me. Okay. Something about that beat is messing me up. Okay. v1 equals 5 minus v2. Good. So we'll say 25 equals 5 minus v2 squared plus 10 v2 squared. Okay. So now we gotta FOIL this 5 minus v2. 5 minus v2 times 5 minus v2. First term outside, inside, blast. So 25 equals 25 minus 10 v2 is v2 squared plus 10 v2 squared. This is still not right. There's still something wrong here. Something wrong here. Maybe not. Let's just keep going. The math isn't wrong. 0 equals negative 10 v2 plus v2 squared plus 10 v2 squared. This cancels out. So v2 squared is okay. I know why it makes sense now. So there you go. There's your answer, Deborah. When you have a big mass here, and it's not moving initially, and this smaller mass moving at a fairly slow speed hits it, this mass isn't going to move at all. It's going to stay stationary. So let's go back up here and plug it in. So v2 is 0, so it means v1 is 5, but that doesn't make sense either. Something's wrong with this. Hard to say, Deborah. Hard to say. You have to take consideration if the car smashes with you inside of it, some of the car parts could go through the body. Yes, it did, Ben. And other time, if it's inelastic, or sorry, elastic collision, it could cause a lot of whiplash. Your head is not going to move with the car. So that could cause problems too. So something's wrong with this. This is why I don't teach this. These people call, it's so annoying why they wait so late to call me. Okay. So let's leave that. Maybe figure out what's wrong with it later. Because I don't ever solve it like this. Because you can see what a mess it turns into. There's an easier way. But mathematically it's easier, but conceptually it's not. So what we're going to do is we're going to solve it for the center of mass approach. We're going to look at the velocity of the center of mass of this system. Center of mass is just a point that you can consider all the mass to be located. So it would probably be somewhere over here, because 10 times this mass is here. So what we do is we multiply the mass times its velocity plus this mass times its velocity over the total mass, which would be 11m. So velocity of center of mass is equal to 5 plus 10 over 11. So it's 15 over 11. Which will let the calculator do? 1.36. So the center of mass velocity is moving to the right at 1.36 meters per second. This velocity is never going to change in this scenario. So if we want to figure out the velocity of mass m in the center of mass frame of reference, that'd be like if you're riding on the center of mass, what would this velocity look like to you? So mass m, we would say that velocity of mass m in the center of mass frame of reference, that little apostrophe, it tells you that, we would take its initial velocity and subtract the center of mass velocity. 5 minus 1.36 is 3.64. And then to get the velocity of that mass after the collision, all we have to do is reverse the sign. So it's going to go backwards at this. Now to get back in the original frame of reference, we just have to add this to the center of mass velocity. We've got to undo the first step. So it's negative 2.28. So that smaller mass is going to bounce off in the other direction at negative 2.28. Now we can do the 10m the same way. Velocity of the 10m mass in the frame of reference of the center of mass, we would get 0 minus 1.36, which is negative 1.36. Velocity of the 10m mass after the collision, we just reverse that sign. And velocity of 10mf equals 1.36 plus 1.36 is, this doesn't make sense. Something wrong here. 2.72, maybe it's not. Huh. Very, very slight difference. Center of gravity is you're dealing with something that's on Earth. Center of mass can be anywhere outside of Earth's or a gravitational field, but it's more or less the same thing, Deborah. So this is right. So let's prove it. Let's prove that this is correct. Sum of momentum initial is going to be 5m. Sum of momentum final, it has to be 5m. So we have mass m times negative 2.28. So negative 2.28 m plus 10m times 2.72. Now if that doesn't add up to 5m, then something's wrong again. So 10 times 2.72 minus 2.28. Something's seriously wrong here. I don't know what's going on with this. Something seriously wrong. Okay, 5 plus 10. Oh, duh. This is what it is. I see it here. This is all wrong. This is all wrong. That's how physics is, people. First 25 times you do a problem, it's wrong. Then you finally figure out what it is. Alright, so let's just get rid of this. This, all of this. This is all wrong. All wrong. All wrong. Okay. This 10m times 0 is 0. So this should be just 5m over 11m. See how one stupid mistake at the beginning of the problem messes you up for the whole rest of the time. So it's 0.455. Now it'll work. Meters per second. Okay, so 5 minus 0.455. .545. Reverse that sign and then add it back. What in the world is wrong with me? I'm rushing, that's the problem. Come on, stupid thing. Alright, let's take our time. So 5 minus 0.455. What's 4.55? Okay, that makes sense. That makes sense. Because center of mass. Okay, I got it. So then we subtract it. We make that negative. And then we add this back afterwards. So it's going to be momentum is just mass times velocity. Talking about collisions, actually there's a couple of different types of collisions. We're only dealing with perfect conditions, like perfectly elastic, perfectly inelastic. But there's obviously nothing's perfect like that. There's always a little bit of an elastic or inelastic component to a collision, or vice versa. Make the sign negative plus add it back. Okay, 0.455. So negative 4.55. Negative 4.095. Okay, so that's how fast that smaller mass is going to be going. It's going to be going back the other direction at 4.1 meters per second. Now we'll get to bigger mass. 0 minus 0.455. Reverse the sign, we get positive. And then we add it 0.455 plus 0.455. That makes sense. 0.91. So that is how fast the bigger mass will be going. So the bigger mass is barely going to be moving to the right, while the other one's going to be going back almost at the same speed it started with. That's right, Shaka. We got it. So now we can see if this worked out. So initially, our momentum, he said, is 5m. Afterwards, it's going to be m times negative 4.095 plus 10m times 0.91. All right, let's see if this works. If this works, then we'll be set to go. So 10 times 0.91 is just 9.1 minus 4.095 is 5. Yes, so we get up to 5M. So it worked. So you can see that this method is much quicker than the other one. I still don't know why the other one didn't work out. Maybe if I'm bored tomorrow, I'll start working on it. In fact, I'm going to take a picture of this and see if I can figure out what my mistake is. Doing it the other way. Take a picture here. My initial conditions, and then we'll figure it out. All right, everyone, that's enough for today. So, thanks for coming in, everyone. Oh, ice cream truck, that sounds good. So thanks, Grace, Katarina, Shaka Cat, Deborah, Ben King, who knows in here, Jamie, Genesis Floods, Dillhole, Greg. Yes, go over to Siski's now for the 3 premieres in a row. Siski, Deo, and then mine. Mine's short. Mine's only 12 minutes today. All right, everyone. Thanks. We'll see you next time.
10.
Let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
This is Mission Control Houston.
Roll program. Roger roll, Discovery.
Discovery's roll maneuver is complete. It is now in a heads-down position on track for its flight to the International Space Station. Discovery flying 365 miles per hour, 1.5 miles in altitude, 7 miles downrange from the Kennedy Space Center. Discovery's engines are throttling down as the orbiter passes through the area of maximum pressure on the vehicle.